2021 annual symposium of the Center for Computational Science and Engineering at MIT. We're really pleased everyone could come. We apologize in advance for our format, but as everyone is these days, we're doing the best we can. As just a little bit of information, so if you've joined directly from the Zoom link, that's great, but there's also a Gather Town where you can interact with all the other participants. So we encourage you to try that out as well. And the auditorium of Gather Town is where these talks are. But as you know, the annual symposium, the CCSE, is sort of our annual way of showcasing sort of top and interesting work in the area of computational science and engineering. We always feature a distinguished external speaker who will have Professor Nick Trefethen, who will be introduced shortly, giving our keynote lecture. Then we have talks from 3 MIT faculty, from Raffaele Ferrari, Wim van Ries, and Bilge Yildiz. And then we'll have a poster session, the awarding of student research prizes sponsored by the MathWorks, and hopefully lots of discussion and mingling and interaction in between. And so we're really happy that you're going to spend the afternoon with us, and really look forward to interacting and chatting as much as our virtual circumstances allow. And Nicholas, I don't know if there's anything that I forgot to mention that you want to add. Or you're muted, by the way.
Big welcome to everybody, and hope to see you next year in person.
Yes, indeed. Oh, and also I should say welcome to the newly admitted students, because I think mixed in with the sort of crowd of people who are already around or friends and affiliates of CCSE are students newly admitted to the graduate programs in computational science and engineering at MIT. So we're really glad that you could come and spend the afternoon with us as well. So with that, I think I'll turn it over to Professor Alan Edelman, who will introduce our keynote speaker.
Thanks, Yusuf. So it's a great pleasure for me to introduce Nick Trefethen, who I believe many of you already probably know. Nick not only taught me numerical linear algebra and spectral methods, but has taught thousands of others through his math texts that are as exciting as any New York Times bestseller, I should say. And that doesn't happen very often with math texts. He's, of course, well known for many things, Trefethen and the inspiration for approximation and Julia, blurring the distinction between the discrete and continuous, which so well deserves to be blurred. I remember well Nick purchasing the first copy ever worldwide of commercial Matlab and handing me a shrink-wrap disk for me to open up and play with on a PC in the basement of Building 2. I think most of all, I and many others are grateful for the example that Nick has shown that it's not enough to do mathematics or do computation, but the highest priority is the communication to other human beings. So Nick, thank you very much for coming. And you're muted.
Not anymore. Thank you, Alan. That was great. I love this idea that I blur things that deserve to be blurred. That's great. Just to say a word about me, I'm actually from Boston, as of course my old friends know, but many of you perhaps don't know, I'm from Lexington. So it's very strange to be in England, where I've lived for 23 years, wishing I were with you back home. Of course, this year I haven't been there, obviously. And this 1-year anniversary has special meaning for me because a year ago you had invited me to speak. And that trip to Massachusetts was something I was looking forward to enormously. I was going to see friends and family and you all, and it was the first of many things that got canceled. And when I think back a year, I remember how we all had the notion that we were going to go through a strange couple of months. And then things would magically revert to normal. And here we are a year later, and with more or less the same attitude that we had in March 2020, that it's a couple more months. So we'll see what happens.
Nick, anyway, if it makes you feel any better, it's 18 degrees Fahrenheit here in Boston.
Oh, wow. Gosh, okay. Anyway, I'm delighted and honored to be at MIT virtually, an amazing place, as you know. Now, I guess I should share my screen, so let me attempt to do that. And now let me try to find my talk. Okay, so you should see from the Faraday cage to lightning Laplace and Helmholtz solvers. Yusuf is nodding.
That we do.
I guess you see that. I'd like to say a word about how this fits into my life. I'm hearing funny noises, so please do mute yourself if you're not me. I'm not so young, and yet in my career, there's really only been 2 times that I've been seriously involved in an application. And this was one of those times. The other was fluid mechanics many years ago, starting at MIT. So really, it's been an unusual thing for me to be doing physics, if you like. And that doesn't happen in my case because I start out wanting to do the application. It comes through indirect routes through numerical algorithms. This was the second time in my life that algorithmic questions led me to a physical problem. And it's a very happy story for me. It worked out utterly fascinatingly. Now, this talk is mostly about algorithms, but the first 15 minutes or so, I want to tell you about the physical problem because it's so interesting. So here you see a picture from the good old Museum of Science in Boston. I'm sure some of you have seen this famous Faraday cage there. You know the idea that cages can protect you from electrostatic or electromagnetic things. So here's a more familiar application, a microwave oven. The starting point is that if you have a continuous metal shell, then there are no potential differences inside it. It's a constant voltage inside a metal shell. And that goes back to Gauss. They're easily proved. So if you have a metal shell, there will be no fields inside because a field is a gradient of a potential. But in 1836, the great Michael Faraday realized experimentally that the same seemed to hold even if you didn't have a shell, but just a mesh of metal. So that's what we call a Faraday cage. It's a mesh of metal designed to keep electrostatic or electromagnetic waves out. And the microwave oven is the famous example where every time you heat something up in there, there are electromagnetic waves, microwaves that are doing the heating. But they can't get out the front door because of that metal screen with little holes in it. The wavelength of the microwaves is a good deal bigger than the holes. On the other hand, light, of course, gets out through the holes because its wavelength is much, much smaller. So every day, every one of us uses a Faraday cage in this context. So that's the famous physical phenomenon. Now, for reasons I'm not going to go into, but I would love to talk about in another hour, I got interested in understanding this. So I figured I would look it up in the books. And in fact, I figured I had probably learned it as an undergraduate in a physics course. I took a lot of physics. I took E&M. And I figured probably they had told me how Faraday cages worked. So I went to look in the books and I couldn't find it. It's amazingly hard to find an explanation of this effect. I looked and I looked, and finally, actually, it was at lunch where a professor here at Oxford told me I could find it in Feynman. So here we have the most famous effect of all of electrical engineering being explained in the most famous physics textbook ever written. So there you have good old Feynman with the Feynman lectures, which, by the way, I've listened to some of. He's wonderful. In one of the chapters of his lectures, he doesn't use the expression Faraday cage, but he explains it. And you can see this figure, and the figure shows the intuition. The intuition is, if you have something periodic like a cage, and you go orthogonally to that, you should get exponential decay, right? A sine wave, go orthogonally in the complex plane, it becomes an exponential. So that is everybody's intuition, including mine, and no doubt it was Feynman as he wrote that bit of his book, probably the night before giving the lecture. Here's a quote from the book. So Feynman writes, the method we have just developed can be used to explain why electrostatic shielding by means of a screen is often just as good as with a solid metal sheet. Except within a distance from the screen a few times the spacing of the screen wires, the fields inside a closed screen are zero. Now, of course, he doesn't really mean 0. He means exponentially small, but you know, that's fine, and that's the way he likes to talk. So this is absolutely the intuition I had, and I think most people have when they think about this. The trouble is, I've been having difficulty making it precise. It took us a long time to realize, but the reason for the difficulty is this is just wrong. It really isn't true. The intuition is wrong. Feynman is wrong. It's the wrong conclusion and the wrong argument. In fact, Faraday Cage effect is not exponential at all. It's much weaker than that. And I'm going to say a little more about that. It's a Laplace problem. Let me go back for just a minute, however. I mentioned there's a lot of story attached to this, and I'm not really going to linger on the story, but one part of the story is that it turns out there's a group of people who curate, if you like, the Feynman lectures. And you know, the Feynman lectures on physics are just a great, great thing. It's a collection of books together with videos and radio recordings that you can find from the early 60s. Really exciting stuff. And there's a group of people that keep it up to date. And when they found out I was saying Feynman was wrong, they were not pleased. And I'm always interested in the logic of the situation. In the end, I was told that the argument Feynman gave was correct. And moreover, he didn't give that argument. It was the co-authors. So I always find it interesting when you find two completely orthogonal arguments to defend something. In fact, Feynman really did get it wrong. It took me many, many months to be confident of that because, of course, we all know Feynman was a smart guy. But as a professor, I know how this works. You do things the night before a lecture, you follow your intuition, you reach something that looks plausible. Mistakes can slip in, no matter, even if you're fine. And moreover, if he were alive to take a look at this, in milliseconds, he would say, oh, of course, yes, that was dumb of me. He would understand the situation and move on. So let me tell you what we learned. It's pretty clear that what's going on here for electrostatics, as opposed to electromagnetics, is a Laplace problem. So let's imagine in 2 dimensions, a Faraday cage, which is a ring of dots, if you like, cross sections of wires in the 3rd dimension. You have a potential field, so Laplace equation is satisfied away from the wires. You have some sort of external forcing thing. I will see if I can even get a pointer. I probably can. Do I have a pointer? Yes, okay. So you have an external field there, and I've made it just a point source. The cage consists of a collection of wires, and what matters is that obviously the wires are connected to one another, off in the 3rd dimension somewhere. So they're all going to have the same voltage. So that's our Laplace problem. We have that the voltage should be equal to a constant on all of these little disks of radius r, which I'll put at the nth roots of unity. And then we have some forcing term, which I might as well take to be just a point. And then at infinity, we have a condition which basically amounts to saying that the total charge on the wires is 0. So the charge within wires can flow around in response to the external field, but there's no net charge on the wires. So I think it's pretty clear that's the natural model of what's going on with the Faraday cage, electrostatics. So now let me show you what the solutions look like. And these are now numerically computed, and most of the talk will be about how we do these computations. Here you see an external source and then equipotential lines. And you can see the shielding from the fact that there aren't any lines inside the cage. But now let's change the radius of the wires. So I'm going to shrink the wire radius from 0.1 to 0.01 and then to 0.001. What you see is that obviously the shielding is weakening. It's shutting off as the wire radius goes to 0. So the model of infinitesimal wire radius can't be right. Now let's also look at how it depends on the number of wires. So here I'll take n wires of radius 0.01. So there you see the shielding with 10 wires is not so great. With 20 or 40 wires, it improves, but it's only improving linearly. There's nothing exponential here. It's just linear improvement in the number of wires. And in fact, when you do the analysis, you find that the dependence on the radius of the wires is logarithmic, and the dependence on the spacing of the wires is linear. A lot of this was done with John Chapman and Dave Hewitt at Oxford, and we wrote up the paper in the 2015 SIAM review. There's all sorts of interesting connections here. If you're interested in stochastic problems and Brownian motion, that gives an intuition about why the dependence on the number of wires is just linear and why the dependence on the radius is logarithmic. It's all about Brownian motion and the space scales attached there. In fact, if there are any biologists in the room, similar things were done by Ed Purcell and Berg back in the 1950s, studying how bacteria communicate with their environments. So where did Feynman get it wrong? So Feynman assumed that each wire had a constant charge, whereas the right condition would be a constant voltage, as of course he would know if he thought about it for a second. With constant charge, it does make sense to speak of infinitesimal radius. Unfortunately, that's not the problem we should be modeling. You want the voltage to be constant across the wires, and you've never heard of a point voltage because they don't make sense physically or mathematically. You can't have a point voltage. The mathematician would say, if you have a Dirichlet boundary condition for the Laplace equation, it has to be applied on sets of positive capacity, not zero capacity. So on mathematical terms, once you think about it, it's clear that the shielding has to fail as the radius of the wires goes to zero. So if you want to know more of the story, I did write an essay about it in SIAM News, and it's on my homepage. The story is a lot of fun. And to finish this bit of the talk, let me, as I always do, give a Matlab demo. So here we are talking to Matlab. And I have a little code called Faraday. And what I can do with this code is click to put a wire somewhere. Nicholas, would you nod if you, or somebody nod if you can see that, all right? Yes, you can. So every time I click, I put another wire in, and it's computing the field generated by that blue dot in the cage defined by these wires. I'm going slowly, not because the computations are slow, but because web graphics is weird. So you can see we're definitely getting shielding. The more wires I put in, the better it gets, but you can tell there's nothing exponential there. It's just linear. So let's finish that off. So in this talk, I want to spend the rest of the time saying a word about how you solve these things numerically. It's all two-dimensional, but it's not all smooth domains like this. We start with smooth domains like disks, but the more interesting stuff is what do you do on more realistic domains that have corners? Okay. So the talk will discuss three approaches. And first of all, I want to say how you can do things like this for smooth domains, for Laplace problems and other related problems. These are ideas which are very classical and used amazingly rarely. I think they're used rarely because computers came along more slowly than numerical analysis. And by the time computers were around to make this stuff easy, numerical analysis had moved on to much more general techniques like finite elements. There you have it. The mathematics is actually based in Runge, 1885. And then I want to talk about what you do when there are corners. And the mathematics there starts from Donald Newman in 1964. And then I want to show you the newest thing, a much faster potentially approach, also for problems with corners. So in all of these methods, we're going to connect real and complex functions. To find a solution to Laplace, a harmonic function, we're going to find the real part of an analytic function. And to find the coefficients, we're just going to do least squares on the boundary of our domain. So we assume we have a problem where all the physics is in the boundary, if you like, Dirichlet-Neumann conditions on the boundary. It's going to always be least squares, so it's all rectangular matrix problems. Matlab / is just fine. In 3 dimensions, issues of scaling of computational time would be a much bigger matter. But in 2D, you don't need parallel computing for these problems. Maximum principles, of course, are very nice, and they will give us a posteriori bounds. And the method generalizes to biharmonic and Helmholtz equations. I don't know what else, perhaps. But as I say, it's all 2D. I'm not showing you anything in 3 dimensions. And I really have no opinion as to the prospects of methods like this in 3 dimensions. It's surely non-trivial. Whether good things can be done there, I'm open-minded. So let's say a word about smooth domains, Laplace equation in domains bounded by smooth curves, which is how I did it for these Faraday computations. So as I say, we're going to find a harmonic function by fitting the real part of a polynomial, let's say, on the boundary. This idea goes back to Joseph Walsh at Harvard, but he was completely non-numerical, understandably for that era. He tried to do everything with square matrices using interpolation. You're going to lose if you try to use square matrices. You always need rectangular matrices and least squares. As I say, the theory essentially is due to Runge in 1885. There aren't that many people who really use this stuff numerically. There are a few examples. And I should say polynomials applies if you're on a single, simply connected compact domain. But once you start having unbounded domains and wholes, then you generalize to rational functions, but it's a trivial generalization. By rational function, I only mean reciprocals of monomials. So you start putting in terms like 1 over z minus a fixed pole, powers of those terms, and you always need to have a log in each whole. I spent a lot of time on these problems in recent years, and I found favorite references for every aspect. For example, the very fact that it all goes back to Runge is not well known, and yet it should be. He's the one. Let me also point out my favorite reference on how harmonic functions connect to complex analysis. It's a wonderful paper by Sheldon Axler, and it points out that if you have multiply connected problems, it's all really the same. Just put 1 log in each whole, and then everything becomes the same. So you don't have to talk about multi-valued analytic functions if that makes you nervous. All you need are 1 log in each whole, and the logs take care of all the multi-valuedness. So I'm going to do some more demos now to show you just the ease with which you can solve Laplace problems in regions bounded by well-behaved curves. So back to Matlab. And these are from a paper I wrote that contains demo code. So for example, one of the codes is called disk1, and it solves a Laplace problem exterior to that blue disk. How does it do it? Well, it sets up a series, and it samples the boundary of the disk in equally spaced points, and it does least squares. If you have a bunch of disks, same business. On each boundary, you sample in maybe 16 points, do least squares. There's a log term and a reciprocal inverse of monomials in each whole, and then and that's all you need, provably, to converge to the solution. If you have slits instead of disks, that's essentially the same. You just turn power series into Chebyshev series, essentially. So slits and disks are not really different. If you have a Cantor set, well, I can't do an infinite one by this method, but here's a little code that does a Cantor set with up to 2 to the 5th components. So you can see for these desktop scale problems, it's perfectly reasonable to use these elementary series methods, and you can get easily 10 digits of accuracy by methods like this in a second. We're always in a terrain here of problems that are mathematically trivial. I mean, there's nothing to say to a pure mathematician about these problems. Now, what about computationally? Well, in some sense, all 2D PDEs are pretty trivial computationally. We all know software that can handle them. But that software is not going to get 10 digits without a lot of loving care, right? If you want to do finite elements to solve a problem like this, or even integral equations, it takes some real attention to details. For these simple problems, there's a lot to be said for the simpler method of series. I wanted then to illustrate another application of these series to conformal mapping. So here's another built-in code. If you want to conformally map a smooth domain to, let's say, the unit disk, that's essentially a Green's function, so it's basically a Laplace problem. And there again, you can solve it by using these series with least squares on the boundary. So maybe I have 200 points on the boundary and I'm solving a least squares problem of size 200 by 40 or something like that. That's how elementary the computations are. One more conformal map. These codes are built into Trefethen, but for no particular reason. This just happens to be the software package I'm involved with. Probably even Julia could handle these computations. Okay, so back to the talk. To finish up the smooth stuff, let me say a word about theory. And that is that you can prove that, in fact, it's easy to prove, it's all essentially goes back to Runge, that if you do things right, everything converges exponentially as you take more coefficients. The official source on this stuff would be Walsh's book on interpolation and approximation. It's an unreadable book. I've never liked this book, even though it's full of all the stuff I've spent my career using. In practice, however, something very interesting comes up. And that is that if you do all this in practice, it will usually fail unless you're working with disks or slits. And the reason is that the powers that you are working with are exponentially ill-conditioned. Now, historically, that would have been considered as a big challenge, and people would talk about Faber-Walsh polynomials or something. But actually, it turns out it's very easy to fix this. All you need to do is the Arnoldi method. So also known as Stieltjes orthogonalization. If you, instead of using a Vandermonde matrix, if you do the mathematical equivalent with an Arnoldi iteration, you can solve all the problems of ill conditioning of these bases. And we have a paper of that written just last year that will come out pretty soon, I guess. I'm actually going to spend 5 minutes showing you 4 examples of how easily and happily Arnoldi orthogonalization fixes the problem of ill-conditioned bases in problems like this. So the first example is, I'm not going to linger on the details, but suppose you want to interpolate a function in the unit interval in Chebyshev points by a polynomial. There you see a interpolant of degree 80 with some bad errors. And there you see the convergence is only going to 2 or 3 digits and then having numerical trouble. But if you do Arnoldi orthogonalization, it goes all the way down to machine precision. Second example, so-called Fourier extension. You have a non-periodic function on the unit interval. You want to fit it by a Fourier series that lives on a larger interval, like -2, 2. We know mathematically that's possible, but how can you do it computationally? Well, if you try to solve that by analytic methods, you get root-exponential convergence. But if you just use Vandermonde with Arnoldi, you get exponential convergence. Third example, suppose you're in the complex plane and you want to find a minimal polynomial on a domain, like a triangle, normalized by being 1 at the origin. So we call that, in this case, a degree 30 Chebyshev polynomial on a triangle. There's an algorithm you can use to do that called the Lawson algorithm, iteratively reweighted least squares. If you just do it as written, you'll only get a couple of digits of accuracy. But as soon as you use Vandermonde with Arnoldi, you get convergence down to machine precision. Notice this beautiful error curve, which is circular almost everywhere, but with the three corners corresponding to the three corners of the triangle. A final example, which is what we're about to turn to. Suppose you're doing what we call our lightning Laplace solver for regions with corners. There's a polynomial term that's part of that solver, and that term will mess you up unless you orthogonalize. And as soon as you orthogonalize, it's fine. I make this sound easy. This is where we discovered it. It took some months of looking before we realized how crucial this orthogonalization was. So here you see, for this particular region, convergence down to about 6 digits and then stagnation if you don't use Arnoldi. But if you do, you get to 12 or 13 digits, and you wouldn't get to 16, but you certainly get to 12 or 13. So obviously I haven't given the details, but if you're interested in these methods, the Vandermonde with Arnoldi technique is an important part of it. So now for the rest of the talk, I want to talk about regions with corners. We started with the Faraday cage, which had the beautiful property that the wires could be taken to be circles. So computationally, that's as easy as it gets. But I think in most applications, you don't have smooth boundaries. Boundaries of most problems have corners in them. And those corners almost always generate singularities in the solution. And here, the theoretical result that we're leaning on goes back to Donald Newman in 1964, what we call root-exponential convergence. So Newman showed that if you're doing approximation theory, looking for rational approximants of the absolute value function on the unit interval, polynomials converge at a terribly slow rate, but rational functions converge exponentially, or more precisely, root-exponentially, this O of constant to the minus root n, which in practice is great. It means if you want 6 or 10 digits, no problem. So there are the curves. Polynomial approximation to absolute x, you'll never get past 4 digits. Rational approximation, you easily get up to, what do we have here? 10 digits, or 8, I guess is shown there. So all it takes is a rational function of numerator and denominator degree 50, and you can match absolute x to 8 digits. And everything is known about these problems theoretically, the polynomial rate of convergence, the rational rate of convergence. What Newman realized was that what makes this possible is that rational functions can concentrate their poles exponentially near singularities. So here, in fact, you see the poles of the best approximation of a certain type to the absolute value function. They're clustering exponentially near the singularity at 0. So that's 50 years of approximation theory. It actually hasn't been used much until the last couple of years to try to solve computational problems. And yet it turns out it's all the same. Within very broad parameters, elliptic problems have corner singularities that can be addressed in a similar way. Certainly the Laplace equation does. So this leads to what we call a lightning Laplace solver. And let me comment on the name, which sounds pretty annoying at first. And indeed, we hesitated to use that name because it seems so annoying. But it's so right that in the end, we couldn't resist it. So the point is, of course, lightning means fast, right? But the point is that lightning strikes objects at corners for reasons of potential theory. You get infinite gradients there. This has been known since Faraday and so on. It's Benjamin Franklin, if you like. The point of this mathematics and these algorithms is to exploit precisely that phenomenon, to use the singularity in a clever way to get a fast solver. And so the logo you see is not just a lightning bolt, but a lightning bolt with a bunch of red dots in it, which suggests we're going to put poles near corners in order to take Newman's approach to the absolute value function and apply it to very general problems in the plane. So this is what we're going to do. we're going to solve Laplace's equation by the real part of a rational function. And the rational function will have a smooth part, which we call the Runge term, and a non-smooth part at the corners we call the Newman term. The Runge term won't really look like this. It will be Vandermonde with Arnoldi to make it stable. So to get our harmonic function, we'll do least squares with a big rectangular matrix. I say big, I mean a couple thousand by a couple hundred typically, which samples our boundary data and does a least squares fit to that data. The sample points are also going to be exponentially clustered near the corners, just like the poles of our Newman approximation. If you want the literature, there it is. We know a lot about how poles should be clustered near corners, and I'm not going into that, but the mathematics of that is very beautiful. It comes down to potential theory. We know just how to cluster them. There's kind of a universal formula that applies to all kinds of corner singularities for the Laplace problem. So I'm going to now demonstrate this with our code you can find at my website, which is called Laplace. So suppose I say Laplace and I ask for one of the built-in demos, like the L-shaped region. Then I will run it twice because the first time everything is always slow. Okay. So what you see here is an L-shaped region, and you see the code has exponentially clustered poles near each corner in order to capture that singularity. The convergence plot is showing root exponential convergence because the x-axis is the square root of the number of degrees of freedom. So with about 250 degrees of freedom, 243, I guess it is, we are solving this Laplace problem to 6 digits, and we really are. That's on the boundary, a posteriori confirmation. It's really 6 digits all the way up to the corner singularity. That took a 1/6 of a second on my laptop, and the resulting rational function representation can be evaluated at 30 microseconds per point. Let's do the same problem, but ask for a higher tolerance. So I'll say tau 10 to the minus 10. So now instead of a 1/6 of a second, it took 3/4 of a second. And you can see the more or less straight line again on the square root of degrees of freedom curve. So we're getting this root exponential convergence down to 10 digits with this guaranteed a posteriori error on the boundary, 10 digits all the way up to the singularities. When you ask for a higher tolerance, it's putting more and more poles near each corner. I can also play around with things like, if I say Laplace of 8, it'll take a random octagon. So every time I do that, you see a different random octagon. And always on the left, this more or less straight line of root exponential convergence. If I say Laplace of minus 8, it gives you a random circular polygon. So there again, convergence down to the default 6 digits in 0.4 seconds. I also have conformal mapping codes based on this Laplace solver in the same way we did it for smooth problems. So for example, if I type in a vector of these 5 vertices, then you see it's computing the map back and forth between a polygon and the unit disk. I think the default accuracy is 6 digits here. And similarly, if I say conf map with a number, it'll give me a random polygon with that many vertices. Or if I say minus, a random circular polygon with that many vertices. So I've had a lot of fun in the last couple of years solving Laplace problems and conformal mapping problems using these techniques. The competitor is really integral equations, which are certainly as fast when wielded by the experts, but the codes involved are much longer and more dependent on expertise. If you want to solve a problem like this to 10 digits with a 60-line code, you want to use these methods. Okay. The theory guarantees root exponential convergence. And the proof here is now quite non-trivial. I won't go into it at all, but it certainly involves complex variables. You need to use the Hermite contour integral representation for rational interpolants. You certainly need to use potential theory. And then to handle the fact that you have multiple singularities, one at each corner, we use Cauchy integrals in a kind of a cool way. And the theory is beautiful, but I'm not going into that now. In practice, again, it's crucial to orthogonalize. And as I say, this is how we discovered the importance of Vandermonde with Arnoldi. Once you do that, you can pretty regularly get 10 to 12 digits in practice in 16-digit arithmetic. So just a couple more pictures illustrating the biharmonic equation can be reduced to analytic functions by a method going back to 1898 due to Goursat. And so these are computations by my student Pablo Brubeck. And again, you see the nice root exponential convergence. Notice in here, it's Stokes flow, the biharmonic problem. You get what's called a Moffat eddy in the corner. In fact, you in principle get an infinite series of eddies. And there's the first one, and there's the second one just coming out of this single series representation involving exponentially clustered poles near each corner. These pictures were first computed at MIT when Einar Rundquist visited Tony Patera in about 1986, I don't remember. That was with adaptive spectral element methods. The Helmholtz equation is analogous, and I'll just quickly step through the analogy. If you want to see it, it's in a short paper written by me and my student, Abhi Gopal. The Laplace equation is that, the Helmholtz equation is that. The scalar fundamental solution for Laplace is a log. For Helmholtz, it's a Hankel function. The dipole fundamental solution for Laplace is a pole, if you like. For the Helmholtz equation, it's another Hankel function. If you want to make a series for Laplace, it's like that. For Helmholtz, it's like that. If you want to do the lightning approach with exponentially clustered singularities, that is to say, Newman and Runge terms, you get analogous things involving Helmholtz functions. And here we have not worked out the theory. We don't have theorems showing this works, but it certainly does. And let's just show a quick example. If I say Helm of 30, it very quickly solves a little Helmholtz problem. And then it takes forever to make the plot. We're waiting for that. So there you can see a scattering around a square obstacle. There are exponentially clustered poles near each corner because of the corner singularities. We're getting about 4 digits of accuracy up to the boundary. The reason it takes so long is that it takes a long time to evaluate Hankel functions. It takes like 10 times longer than evaluating just poles. Now I should begin to see the end in sight. So to tell you where we've been, we've done 3 of the 4 parts of the talk. There was the Faraday Cage motivation and application. There was series solutions involving smooth boundaries, going back to Runge. Then exponentially clustered poles, series solutions involving rational functions, going back to Newman. Finally, I want to show you something that has come up during the lockdown of the last few months, actually, what we call log lightning approximation, which holds out the prospect of improving root exponential to exponential. And this came from nowhere. Kind of hard to believe. So the idea would be that in the end, a singularity would come with almost no cost at all. And this is joint work with Yuji Nakatsukasa at Oxford. And the idea is, instead of approximating by a sum of simple poles, we're going to approximate by a sum of reciprocals of logarithms. If you have just one singularity, it would look like this. So there you can see 1 over logarithm minus some number. If you have m singularities, it will look like this. We're going to pick the singularities a priori in a well-ordered way. We're going to find the coefficients c sub jk with linear least squares. So you end up with a method that's very similar in structure, but instead of leaning on rational approximation theory going back ages, it leans on nothing. I don't know anyone that's ever looked at this, and it came out of the blue, as I say. So here's the blue that it came out of. If you want to approximate a singularity like z to the a on that interval, well, one way to do it is to change variables. Take a log. You find you have the problem of approximating e to the as on the negative real axis. Well, that's a famous problem in approximation theory. That was made famous by Cody, Meinardus, and Varga in 1969. The convergence rate is exponential for that problem. So we've suddenly, just by a change of variables, reached the startling observation that to approximate one singularity, we should be aiming for exponential, not root exponential. Now, if you have a bunch of singularities, you're just going to add these things up. I'm sorry, I'm speaking a bit fast. Sorry, if you have one singularity, the rational approximation looks like a rational function on the negative real axis. But going back with your change of variables, that looks like a sum of reciprocal logarithms in the other variable on the unit interval, or on the interval 0, 1. And now I'm, of course, going quickly, but there's a paper if you want to read it. The way we're proposing to proceed here is we're going to approximate a function by a function with a small finite number of parameters. If the thing we're approximating can be analytically continued around the corners to a multi-valued analytic function, then we can show that when f is analytic throughout the plane except for that branch point, you get exponential convergence. And if f is analytic throughout the complex plane except for a finite set of branch points, so we now have a multi-valued analytic function with a finite set of branch points, then you can prove you get root exponential convergence. So I'm quickly showing you more or less all the experiments we've done. It's a baby here. Sure enough, if we're approximating the square root of x on this interval, the lightning approximation that Newman discovered, which is so fast, is nowhere near as fast as the log lightning approximation. And here I'm doing that in two different ways. One using singularities in the S variable spread out along a Hankel contour, and the other using confluent singularities. They both depend crucially on using van der Maan with Arnoldi orthogonalization. So weirdly, none of this stuff would have worked 2 years ago for silly reasons, because people hadn't noticed the van der Maan with Arnoldi technique in its proper generality. So, of course, the idea would be to solve PDEs, right? Can you solve Laplace's equation? Well, we don't know. We've literally done one experiment. I want to find a student to work on this. So let's go back to good old Laplace equation on an L-shaped region. The one experiment, it took a little care to make it work, but it does work. The lightning solver, which is very fast, can get you 10 digits with about 1400 degrees of freedom. But the log lightning approach gives you those 10 digits with about 600 degrees of freedom. And you see what looks like more or less exponential convergence. So my guess is getting this to work, it's going to involve some attention to stability issues, which I trust will be solvable, but I don't pretend it'll work the first time. If these experiments took half an hour, I'd have done more than one of them. But I think there's a pretty good chance that this will end up as a robust technique once we put in the time to make it work. Now I'm done except for a bit of philosophy and then saying goodbye to you all. I was looking at who's logged on watching this talk, and it's really striking that I know a few of you, but the great majority I don't know. Most of you are presumably students or postdocs, I don't know. Growing up in a completely different world from the one I grew up in mathematically, the biggest single difference is that now every problem has probability in it to an almost laughable degree. The world isn't that probabilistic, but we can't resist. It's so interesting. So here I've given you a talk with no probability in it, and that takes courage these days. My concluding observation has to do with how we formulate problems of analysis and partial differential equations. I believe that most problems of computational science are analytic, except for isolated singularities. In 2D, those might be points. In 3D, they might be lines, for example. And the whole idea of lightning solvers exploits that. For example, here we have again the L-shaped region, and we've solved a problem on it. And I've taken the computed solution, and I've plotted it not only inside the domain, but analytically continued outside the domain, because that's the kind of representation we're getting. We're representing the solution with a bunch of poles outside the domain, so we could evaluate it anywhere. The reason for seeing the circus tent, this is due to the polynomial term in the lightning approximation, but the other stuff is thanks to the rational term, and in particular, you notice along here, the poles are exponentially clustered, approximating a branch cut. And that's what's going on all the time with these solutions. Rational functions, or indeed reciprocal log functions, are approximating branch cuts in interesting ways. Now, this is not the way people normally do analysis, and it's not the way people normally do numerical analysis. It's very rare for people to say, let's have a domain and hope that we can analytically continue the solution across the boundary. That's considered sacrilege in analysis. You would not assume that. The point of view in mathematics is that functions don't have that much regularity. You're lucky if they have a little bit. I believe that in applications, they do have regularity apart from singularities. At least science applications. Notice I didn't say computational engineering, which might be a little more complicated. What do people do instead? Well, both in the theoretical world and in the numerical world, the completely dominant mode of thinking is Sobolev spaces. So people talk about what Sobolev space your data might live in and what Sobolev space your solution might live in. And for example, what finite element spaces you might need that would respect those Sobolev spaces. I believe that that kind of analysis is very beautiful and very natural and does capture something real about the structure of problems. However, I also believe it's obsessing about the wrong thing for most applications. It's obsessing about the notion that functions have very little regularity. You're lucky if you've got a derivative, and boy, if you've got 3 derivatives, you're very lucky. They are not recognizing the situation where a problem is analytic apart from bad points. And I believe that that has skewed our thinking, both in theoretical analysis, where it's just astonishing how analysis is dominated by regularity questions that have nothing to do with this kind of computation where the functions are essentially analytic. And also in numerical computation, it completely dominates the way people talk about finite elements, even though, again, at least in science problems, the domains are usually simple enough that probably your function is analytic away from a few singularities. So there you've heard some strong views. I just want to finish by saying how much I love Boston and MIT and how much I wish I were there. And thank you all very much.
Thank you, Nick, for a really wonderful talk. Very, very interesting. I think we have plenty of time for questions, so I would just open the floor for questions, and people can feel free to raise your Zoom hand or just unmute and speak.
Wow.
I'll start things off with one quick question, which is, do you see any hope now for dealing with Laplace or Helmholtz with heterogeneous coefficients using these kinds of methods?
I guess I would be honest and say I don't expect that. Now, I'm not an expert in the possibilities. I know that, if you talk to Leslie Greengard and other integral equations people, they will claim that even with heterogeneous coefficients, theirs are the best methods. By analogy, I should be making such a claim, but the truth is, I don't know enough to say that, so I won't make that claim.
Yeah. Makes sense. Yeah.
Yeah, I'll ask one. My name's Matt Camone. I'm from Lamb Research, and I'm also a MIT alum from Jacob White's group. Just more of a historical question is, with all the finite element solvers for electromagnetics out there, how come nobody for Feynman's problem, nobody commented on the fact that it isn't exponential? That must be known in the community.
Please do track down that essay I mentioned in SciAm News. It's astonishing. As I mentioned, here you have the most famous effect in electrical engineering discussed in the most famous physics textbook ever written. I mean, it's astonishing. Now, obviously, somebody designs microwave ovens. So there are engineers out there who have measured this stuff. And in some way, they must know what's going on.
Okay.
But I have made zero contact with those people. A sad lesson to learn from this, for those of us who are essentially mathematicians, it's a pretty strong bit of evidence that engineering can do the right thing without paying any attention to mathematics. Let me say one other thing. If you try to look up the literature on things related to the Faraday cage, you'll find lots of papers on much more complicated things. For example, usually electromagnetics rather than electrostatics, all sorts of extra complicated effects. And the papers say they've nailed them, and maybe they have, I don't know. But sometimes you would think that complicated things would rest on a foundation of simple things, but sometimes the complicated things are just there without the foundation.
Yes. Okay. Thank you.
Could you say a few words about the third dimension?
The first thing to say would be pessimistic. So in 2D, all we need is to cluster points near singularities. That's a very well-bounded problem. And with a few hundred singularities, I can nail all sorts of stuff. Now, in 3D, very typically, you'll have weak singularities along edges, if you just think of a cube, right? So the idea of clustering points there sounds like a loser. However, two things. One thing is that the corner singularities are probably much stronger. So it may be that although theoretically you have a problem there, it's surprisingly weak. And the other thing is, I really don't think this has been investigated at all. There's a lot of what people call method of particular solutions, method of fundamental solutions, which does scatter singularities about. But the idea of scattering singularities that are clustered in a priori intelligent way is sort of not there so much. So my guess would be that eventually there are interesting prospects in 3D, but I don't pretend it's going to come quickly. I think that'll be a few years down the road when a few theses have been written on that subject.
Oh, hi, Nick. Sorry, I just had a quick question that's maybe a little blasphemous. But I guess if you get rid, maybe this is like a very bad hack or approximation, but say you wanted a fast solution, could you get rid of the corners by just kind of putting in a very smooth, rounded corner and then use an existing solver, or would you need too many degrees of freedom?
Well, you could certainly do that and get something. Sometimes the result you get would indeed be very accurate away from the corner, and other times it wouldn't be. And I'm afraid you'd have to do some analysis to know which of those cases you were in. For sure, in practice, that's what people very often do, of course. You throw a finite element code at something, and it's pretty good away from the corner. No way am I going to beat the finite elements for 3 digits, but for 8 or 10, it makes a big difference.
Well, thank you.
I wish I could do a
Maybe-
poll. Sorry. I'm asking you a question now, but I don't know how to execute it. I'm really fascinated by the move to probability. And let me give an example. Many of you, I'm sure, know my linear algebra book with David Bao, Trefethen and Bao, right? So David Bao was a student of mine at Cornell who left early. And then, as I'm sure some of you know, decades later, when he was a successful IT expert, went back to MIT and did his PhD in computer science, and just finished it a couple of years ago. And David Bao told me that there was one absolutely dominant difference between computer science in the 90s and in the 2010s, and that was that probability had taken over everything. So what I wish I could do with this audience, and maybe Nicholas, you can tell me if there's a way to do it, I would like to know what fraction of the people in this group are working on things that have a probabilistic component. How do we take that poll?
There's probably a poll.
There is. Kate, do you have a poll feature at your disposal?
Or people could just raise their hands, I suppose, but I don't know.
We can do it more
Oh, yeah. So, yeah, so you could put up your Zoom cartoon hand if you use probability.
So not your real hand, your virtual hand.
Yeah.
I see. Now, what are we finding? Oh, it's going in order. I see. I thought it was 100%, but now I realize if people raise their hand, they go to the top. I see 11, 12, 13. I see a real hand as opposed to virtual. So these are people who are doing things related to probability. Okay, so, oh, and now it says end polling. I promise all of you that that this is a simply astonishing change in the intellectual landscape. It was not like this 20 years ago. Is it as it should be? Is it not? I believe it's a mix. I think partly it's right and partly it's fashion, but it's really astonishing.
And we have a poll in progress.
What is it? Yeah. So that's, I didn't know you could do polls in Zoom.
Yes.
And by the way, I happen to know any problem with randomness in it is addictive. It's very hard once you start to stop. There's a magic about it. So for example, while I'm on this random tangent, I was examining a student the other day, an MS master's student, and the beginning of their discussion said that people used to use differential equations, but recently it has been realized that one should use stochastic differential equations instead. I thought, well, I'm not quite sure computational engineering has gone quite that far yet.
So,
Oh, wow. It's 2/3 or nearly. That's amazing.
Yeah.
Sid wants to say something?
Great.
Nicholas, if I can be heard, yes, I would like to make a brief comment about someone who's in the materials community, and in answer to the speaker, which you've given an excellent talk. The reason I think some of us are interested in probability is the fact that if in materials, real systems, you like to design things that perform up to specification.
Yes.
So you have certain expectations. But in reality, when you put the material component, whether it's a nuclear reactor or whatever it is not under control.
Yes.
In other words, you know, if you're a geologist, you go out and dig for oil and look for oil exploration. What happens when you talk to people like Schlumberger is they tell you the local field, the condition as you encounter could be over-dominating.
Yeah.
And if I may now take an example, very simple example in fracture mechanics, some of us are doing, in materials, we worry about failure like a dam or something. So at what point do you hit that instability?
Yes.
You'd like to be able to predict that. Unfortunately, the prediction is based on equations, as you say. When the equations are deterministic.
Yeah.
They're not stochastic, they're not probabilistic. And yet, in nature, when in real performance, when in actual situations, local conditions matter.
Yeah.
And you can quite often, with this, you know, an innocent singularity nearby a tower or something, can completely screw up your well-designed system. So for the engineers, there's no way you can really handle that except to sort of take your best guess Green's function solution and try to smear it over some kind of a realistic distribution that you're likely to encounter.
Yes.
Well, what we find these days is that more and more of the phenomena we are interested in are outliers. They're no longer within the Gaussian domain space, like, you know, central limit theorem tells you if you do enough sampling, you get to a Gaussian. And it's always the outliers that hit you because they're so costly, they're so damaging.
Yes.
So this now becomes a problem of extreme mathematics, if you like. You know, it's really the outliers that control everything, because once they happen, like an earthquake, then everything else has changed.
Yeah.
So
Thank
how
you.
to deal with the uncertainty is part of the problem for the engineers.
Yeah. And of course, you didn't say, but we are all thinking that 30 years ago it wasn't possible. We didn't have the machines, but now it is possible.
Right.
Thank you.
And any other comments? I see some hands up. Are they leftovers from before? It looks like it. Any other comments or questions for our speaker? Thank you very, very much for a wonderful talk.
Thank you all.
So now we can we go back to Gathertown, or we stay here for the next speaker.
Both. So the next talk is at 2:30, and everyone is free to mingle in Gathertown in the meantime. And if you're in Gather and you move yourself to the auditorium, and then I think you should be brought to this Zoom. So somehow these are linked if all works according to spec.
So we'll see you here at 2:30 for the next speaker. Thank you very much, Professor Trefethen.
Thank you.
Very much.